Hi, I'm Mikey Jeanson, a gameplay programmer with a background in Unreal Engine and C++. I've helped make several games including Your Average Bear, but now I'm a full-time UEFN developer, and this is Verse Boost. Hey guys, welcome to Verse Boost episode 13. Today we're going to be talking about Spawn and Task. Maybe they're your new secret weapon. If you go to the documentation on the website, you'll see this image and it's a little bit, lacking in some of the information. It's not so clear. I wanted to go over it a little bit more. So as we have the same setup and we have expression 0 and it will immediately do expression 1. So this is all in the same simulation update, same tick. And when you do that, a task will be created. So a task is awaitable, and we'll talk about it in a little bit more detail, but basically you can call Task.Await on it. This expression 1 will continue to execute until it gets to a sleep or an await. And just remember, we're on the same simulation update. So as soon as we get to the sleep or await, it will stop executing this function, expression 1, and then it will toss it back over to expression 2. So this is how the thread will operate. So you notice that in this time flow chart, it's not simultaneous. In the documentation, the image is a little bit misleading. It threw me off back when I read it in 2013 with this vocabulary right here, simultaneously. The time flow chart is correct, right? How everything is operating, but it's actually not simultaneous. It's picoseconds later. It's the same tick. It's the same simulation update, but it's not simultaneous, right? And the time flow is correct, but I think it's just this vocabulary that threw me off 2 years ago. So we're still on the same simulation update. We'll finish expression 2, we'll keep going, and then, we'll continue on our way. But here we're waiting for sleep or await to finish, and then we'll continue once that's triggered. And then finally, when it ends, the task for expression 1 will be marked and signaled as complete. So if anything was waiting on task, like await, it will be signaled and it will continue execution. And like I say here, expression 2 and expression 0 are the same simulation update like we talked about. So task is not like most awaitables. If a task is completed before await is called, it will not stall the execution. So if the task is completed, await will immediately execute. It won't wait and it won't be stalled just waiting for the task to complete. It's smart enough to know that it's already done. You can continue execution. Alright, so we're in Verse, and the first thing we're going to do here is spawn a bunch of tasks. So we're going to use spawn, and then you can see it returns task and it's void for this type because doTask, the method that we're calling here, is returning void. So you see we have an array using array comprehension, and then we're going to go through each task and await it, and once it's done, we're going to complete. And you'll notice that each task is going to wait a random amount of time before it sleeps. So we ran the code, and you can see in the top left that they all started with a random different time, and then you'll see that they all complete in sequential order. Just to show that the task.await will not stall, I have added the sleep 1 here, and then I also made the sleep time always -1, which means it will just skip over this and it will run this instruction immediately. You can see when await is called, the tasks do not suspend, they just execute immediately. And notice that the order is preserved. So tasks don't stall, and that's because there's probably something going on like this in the background. This is like just a basic example of how await works probably. So you would call await, and if it's already completed, then it will return immediately, and if it's not, then it will suspend like you would on an event. And now I want to talk about batching tasks. So a task can be batched together to maintain balance on a CPU. We can write like do 5 tasks now and then 5 tasks later. Let me show that in Verse. So I've got a couple of batching methods. We just got some no tasks, no batching, and then start, then wait, and then batch by batch. I'll show you what those guys mean in a second. But first thing we're going to do is look at the start, then wait. All we're going to do here is just start all the tasks as soon as we can, but we're going to take breaks every time this modulo expression equals 0. Then we await all the tasks, and then we print we're done. This technique would be good if you need to run all the tasks before processing results. And also it's important to note if due task is slow and it takes multiple simulation updates and seconds between batches isn't tuned correctly, then you could have batches tripping over themselves where it starts off good, but then because it's taking so long that the others start to catch up and start hogging the CPU, and you don't want that. So if you do have that problem, you might want to do something like this where you're going batch by batch, and this will create a batch of tasks. So you'll use batch end and batch start to basically get a batch, spawn all those tasks, and then wait for all of those. And let's say in this case it's like 10 or something. So you spawn 10 tasks, then you wait for those 10 to finish, and then you increment your index and then start over. So this is good because you're only having 10 due tasks available at a time, right? Instead of managing when you start the due task, you're actually managing the whole lifetime of due task. So this is a lot better for resource management. So using ticks per second, we'll compare start then wait and batch by batch and see how they differ. So you can see that ticks per second is at 8, and that's because all these batches are kind of stepping on each other and they're not running that efficiently. They're probably doing too much work per tick, and that's why it's slowing down the simulation updates. For batch by batch, you can see right away that we're getting 30 frames per second, and like I said, it's much better for resource management because you don't have tasks tripping up on each other. So the trade-off obviously here is that you're not doing it as fast as you would be if you did start then wait. If you're doing start then wait, you obviously are doing as much work as you can, and if you're doing as much work as you can, you're going to finish this faster. But this is spreading out the work to make sure that the work isn't taking up too much of the CPU so that your players can have a smoother gaming experience. So lastly, I want to use some real life examples. These are all methods that I use personally for games that are in production right now. So the way I think about these tasks is like a shotgun start. I don't know if you guys play golf that much, but it's basically starting all of these on the same simulation update, and then we'll wait for them to finish here. But they're all starting at the same time, the same simulation update. And then this next one's pretty straightforward. I just spawn a task. That task might take, several simulation updates to finish. So I've got to wait on this event. So I wait here for it to finish, and then I continue execution. But it's pretty simple. It's just used to make sure that it's ready for the score to be finalized and signal that event. And that's going to be it for the video today, guys. Leave a comment if you have any questions or hit me up on Twitter. And if you liked the video, you know what to do. Thank you guys for watching. Hopefully I showed you guys something new. Have a great week. Peace.